Now we're going to be talking about this weird thing called adverse yaw, Dutch rolls. Like, what is all this stuff? So, adverse yaw. Adverse yaw. So, you can't, nothing comes free in this world, not even lift. So, if we have lifts, oops, we have two types of, well, actually, we have two types of drag. We have parasitic drag, and we have lift-induced. Lift-induced drag. Parasitic drag is literally drag that we're probably most familiar with. So if I have an aerodynamic foil like this, then I have a ball that looks like this, and then I have a little plate that looks like this. If I were to take this and I were to go put it in a wind tunnel, and let's put the wind, and it's going to go all like this, and you can see how it's nice and streamlined. There's hardly any drag at all. But on this one, it's still a little bit of aerodynamics. But right here, you can see how there's potential for a little bit of drag right there. Not much, but there is a little bit. Now we get to this guy, and there's just nothing but drag. I mean, this is like, you know, tractor trailer, you know, trying to haul going up 200 miles down the highway. There's no way unless you got a super powerful engine. But you can see how there's a lot more drag here. There's a little less drag because there's a little bit more aerodynamic, and there's almost no drag here because it's very streamlined. This type of drag right here is parasitic drag, and there's different types of parasitic drag, but we'll get a little bit more into that into the commercial. But for now, let's just worry about the basics of parasitic drag. Now the other one is induced drag. Induced drag is a product of lift. So if you were to stick your hand out the window while you're going down the highway and you put your hand like this, you're actually going to create lift. You're pushing air down, and the air is going to go up. But anytime you have a lift, you have a product of drag called lift-induced drag. So the more lift you have, the more drag you have because of that lift. Now let's say that our ailerons is actually, let me draw right here. This is actually a perfect example right here. All right, so we're looking down on our plane. Now we are going to turn to the left. So in order to turn to our left, this aileron has to go up. This aileron goes up, and this one goes down. So this one's gonna go down like so. Now, as I said, the wind's gonna hit this, causing this wing to go down. The wind's gonna hit this and cause this to go up. The same exact way how you can put your hand out the window. The ailerons act the same exact way. So this one's gonna be going down. Now, as I said before, because of lift, you're gonna have drag, which is called lift-induced drag. So this part of the wing, even though it's being lifted, it has some drag there. And notice what the airplane's going to be doing. What you're going to be experiencing sometimes is when you turn to the left, the aircraft wants to go to the right. Why? Well, because you have a lot of induced drag on this side. That's why we have to apply rudder in order to maintain coordination of that aircraft. Same exact thing, vice versa. If I'm going to go to the right, that aileron's going to go down, this one's going to go up, and I'm going to turn to the right. I have some induced drag on this side, so what is going to happen to that wing? It's going to pull this back this way. That's why we need rudder to go back, to have the airplane go back to the right. So that is adverse yaw. So what can we do to prevent that or alleviate so much drag on the aileron that's going down? Well, what we can do is if it's going down that much, well, why don't we just not put it down so much, and let's go ahead and put this up a little bit higher. Wouldn't that work? That's absolutely right. And these are called differential ailerons. So in the side view here's our wing right here. So on one side of the one that's going up is going to be going way up here like this. There's going to be your aileron. Now, if you go to the other side of the plane and you measure how far down it's going, you're going to notice it's not going to be the same distance. In fact, the other side is actually going to be more like this. If it's the same, you can probably see if it was the same, it's going to have that much drag. So let's reduce that induced drag by reducing how far the aileron goes down. And these are called differential ailerons. The easiest way you can remember this is they move at different distances. So we have differential ailerons. And the other type of ailerons is we got the fries type ailerons, or freeze type fries. It's spelled like fries, but it's freeze, whatever. Anyway, so the other type of ailerons we have is what happens if we don't have that capability to have differential ailerons. It's mechanically, they can't go, this one has to go down the same length, the same height as this one goes up. So what can we do to equalize the amount of this drag? Is there any way we can apply some drag over here on this side so we can equal out the drags? We sure can. On this, the leading edge of the aileron that's going up will actually protrude through the wing, which causes parasitic drag. Now, let me go ahead and draw this and see what this looks like. So we have our wing here. And then the aileron that's going up right here will actually protrude through the wing a little bit. So when you're flying through the air, the wind is going to smack this thing, and then it's going to cause parasitic drag. So if you have lift-induced drag on this side pulling this back, and then you got parasitic drag on this side pulling this back, well, you have even drag. And this is freeze-type ailerons. Now, what type of ailerons do Cessna 172s have? Let's find out. All right, so here I'm going to demonstrate. This right here is, obviously, we're not in a turn, right? However, remember I said when it goes up, it's going to go a lot higher than it goes down, right? So let's go ahead and measure. I'm going to use my pen, and the flaps are at 0, so I can do a little bit more accurate a measurement here. And there it is. There's the distance. Oh, let me go up a little bit higher. There we go. There's how high the aileron actually goes upwards. Now let's see how far it goes downwards. Look at that. So I'm going to put this up, and that's how much more the aileron goes up than the downward motion. So you can definitely see the difference there. I'll do this again. I'll remeasure it just for the bottom part of the aileron. So right about there, that distance. Now I'm going to move it upwards. Look at that. So we have differential ailerons for our Cessna. But wait, there's more. Remember how I mentioned that the leading edge of the aileron can actually protrude through down here, so it actually creates parasitic drag. And that's exactly what happens here. So not only do we have differential, so you can see that it's higher over here, and it's much lower it's not as low when it comes back down. But when we go up here like so, you can see the nice smooth airflow will be in the bottom of the wing until it hits this right here. Let me go ahead and zoom back here a little bit. Until it hits right there. It's literally hitting the bottom of the leading edge of the aileron, and that is disrupting airflow, causing parasitic drag. So your Cessna 172 actually has both types of aileron, differential and freeze type ailerons, all built in one. So now that we know the types of ailerons that we have, now we don't really have to get too much into this part, but flaps. Again, this is a little bit more toward commercial, but there are different types of flaps that each aircraft have. For example, there's plain, there's split, there's slotted, there's Fowler. So what kind of flaps do we have? So really basic. I'm just gonna do this really simple. Actually, I'm gonna do the wing at an angle of attack as if we're landing. Our Cessna has slotted flaps. and your aircraft may be a little bit different, and how you can tell which flaps you have is it's right in the POH2. I want to say it's chapter 8, I want to say. But you can find out all that information in the POH, at least for the Cessna. Now, as we are coming into land, and we're using our flaps. So we're going to have our flaps down, just like so. But the more angle of attack we have, the airflow is going to not stick to the wing as well, and there could be a potential of getting a little bit instability with your wings. So what you can do is you can actually have all this airflow, and you can actually have it kind of rejoin this airflow, and it'll help pull that airflow back and reattach it to the wings. Now how it's going to do that is it's going to have your wing is going to be literally shaped like this, and it's kind of like, oh, actually let me that was a horrible drawing. There we go. So you can see how airflow can actually come up from the bottom and up through here and then reattach this airflow so it'll actually still stick to the wings, so you don't have that shudder when you're actually coming into land. This is slotted flaps, and this is actually what we have, and let's take a look at those right now. Alright, so as you can see at the very top of the wing, the airflow will be coming here, and it will start to separate from sticking from this wing, as you can see. However, if you look in there, you can see the airflow coming through here. And that is how we have slotted flaps. Just look out underneath here. And you can see that too. The airflow can actually go in there. Okay, so now that we understand adverse yaw and the types of flaps and the ailerons, now what we're going to be doing is applying this. What do we have? What do we mean by when we talk about Dutch rolls? So now we're going to be talking about Dutch rolls. So now we understand if we have an aileron that goes downwards, this one's going to go upwards, this one's going to go up like this, so I'm going to right turn, right? So as I'm turning to the right, again, this aileron is actually producing drag, right, as it's getting lift. So as I'm getting more lift, I'm getting more drag, so my nose is actually going to be yawing to the left a little bit. Now what happens to the wing on the right side? So this is going to be going up, it's going to be going down. So as this wing is going up, is causing drag. Now this wing's going to be pulling back. Now what happens when we don't use rudder at all, if we have no specific flaps or any kind of or anything that can help us with adverse yaw? When this wing goes up, this wing is going to have drag due to induced drag. As this wing goes back, look what's happening to this wing. It's actually going through the air faster than this wing. So essentially this wing is going to end up with more lift as this wing pulls back. So if this wing goes backwards, this is going to get more lift. What happens when you get more lift? This is going to go up. Oh, but when we have a lift, we have lift-induced drag. So now this wing is going to be going backwards. Now that this one's going faster, this is going to be going up and you're creating more lift. Now that we have more lift, this is going to be pulling backwards. And it's just a constant, it just never ends. This is your Dutch roll. And in order to prevent this, we have to coordinate our turns with rudder. So that's what a Dutch roll is. Don't really have to worry about that too much on a Cessna. I've actually tried it myself to purposely put myself in a Dutch roll, but unfortunately, because the aircraft is so darn stable and we have some great ailerons that prevent that from happening from adverse yaw, you don't really notice it too much in the Cessna 172, at least for me, at least for my part. But That's what essentially what a Dutch roll is, and you must know it because it's in the ACS. And by the way, all the other information that I've told you so far, as I've always mentioned before, know where to reference this stuff. All of the stuff I'm talking about aerodynamics is all in the PHAK. So go ahead and check out that, the Pilot Handbook of Aeronautical Knowledge, and it's going to be right in there. Now, don't go too in depth into it. Only look at the subjects in that chapter, in the aerodynamics chapter, that is tied to the ACS. So for example, there's the lift equation, there's the drag equation. For the private pilot level, you don't really need to be studying or don't really need to be knowing that kind of stuff, because it's just extra information that you're not going to really need anyway for the checkride or for your private pilot license. So, however, when you start getting into your commercial checkride and your commercial license, that is when that's going to be a little bit more relevant to you. So next we're going to be going over the 4 left turning tendencies. All right, so we have the left turning tendencies. So we have 4 of them. So we have P factor, or propeller factor. We have torque. We have spiraling slipstream. Oops. Spiral. And finally we have gyroscopic. Just gonna put gyro there. Okay, so P factor, torque, spiraling slipstream, and gyro. Let's first start out with P factor. There's been a lot of a lot of common errors about P factor. P factor only happens with high power settings at high angles of attack. Let me show you what I mean. How does the propeller actually get thrust? It works just like a fan. If you were to turn a fan on, and you would actually feel the air blowing at you. Well, if you turn that fan on at 23,000 RPMs, then you're probably going to get a lot more air at the same time as a result. That air, we can call it as thrust. So I'm going to use this paper as an analogy as my propeller. So if you were standing in front of me and this is my fan and I wave it in front of you really fast like that and I go like that, you would feel air coming at you. I don't know if you're hot in here, I don't know, can you feel that? Anyway, so you would feel air because I'm moving the air toward your direction, because I'm angling this at a certain way so you can actually get that. The propeller is designed the same exact way. You see how these are kind of like at an angle right there? They're not like this, they're not like that. They're actually the same exact bite of air. This right here, I'm doing this I'm literally getting bites of air and I'm throwing it at you. That's why you'd be able to feel, if you were here, you would be able to feel that in your face, because just like right now, I'm feeling a bunch of air in my face. This right here, my checklist is actually getting a bite of air and is pushing it at my face. This is what I'm feeling. If I can do this at 23,000 RPMs, then I'm gonna get a lot more air, and we can actually call that as thrust, a byproduct of thrust. So, however, if I were to move this bite of air to this way, I wouldn't be feeling anything. So if I were to take this, you feel that, but if I maneuver it like this, and or if I can do that, you're not gonna feel anything, right? So this works the same exact way. As you can see, I'm trying to get this little eye level here. So if you can see, this right here has a nice bite of air. You can see the width of that, and you can see the width of this. Now the propeller moves clockwise from the pilot's perspective. So if the propeller was like this, it would actually spin clockwise. It would spin, well, okay, I'm gonna get rid of this. Anyway, you get the point. It would spin this way, right? So let's actually take this and let's look at this from a top-down perspective. So as you can see, I'm gonna spin this kind of fast, and I'm gonna spin it, and as you can see, it's the same bite of air on both sides. Same bite, same bite. However, once we Go ahead and put this back on the plane so you can see what I'm talking about here. Alright, so here's our plane right here. Now, and then this is like this. So I'm going to add angle of attack, right? I'm going to add angle of attack, and look what's happening here. As I add angle of attack, look what's happening to this bite of air versus this one. This has a heck of a lot more bite of air slash thrust than this side. This side is just slicing up through the air. So if I'm going forward, where's my plane? If I'm just going forward, high power, high angle of attack, and this ascending blade is only getting that much bite of air, right? And then the right side of my blade is getting a heck of a lot of bite of air. Now let's put this into perspective. As I'm going through the air, this one's just slicing through the air. It's not getting much bite, not getting much thrust at all. However, this side is getting a lot more bite of air than this side. So what tends to happen is, if this is getting more thrust on this side of the propeller than this side, what happens is the propeller is going to actually want to go like this, because you got more air pushing on this side than the left side. So let's see what this actually looks like. So you got your propeller here. In reality, this is what it's going to look like going through the air. And the other side is going to kind of look like this. So as this is getting so much thrust, way more bite of air, this is this, right? But over here, it's this. I can do this as fast as I can, but I'm not gonna feel anything coming my way. And that's exactly what's happening here. There's absolutely nothing. So what happens is this is going to end up going over this way, because it wants to go over to the left. This is P factor. Now remember, you only have P factor high power settings with high angle of attack. So when we start getting into power on stalls, we'll get back into this, because all of these will have a very significant effect on the left turning tendencies, and you'll know why you have to input a lot of right rudder when you're doing power on stalls. So this is P factor. Moving on to torque effect. Now this is Newton's third law. Every action has an equal and opposite reaction. So if I have this propeller and let me go this way, and it's spinning that way. Well, if I'm not really sitting on the ground, if I have something going that way, my natural reaction would be going to the other way. And I can actually show you a picture in the P-hack right about now. As you can see, this is the action. The propeller is moving, and the reaction of the plane, the whole airplane is actually wanting to twist the opposite direction. That's due to the torque effect. Just imagine if I had like a big old propeller in front of me right now, and I wanted to push it this way. My head just did exactly well, that was actually by mistake. So if I were to go this way, my body would actually want to go the other way to try to compensate from this torque, right? So that's exactly what torque is. And again, so the faster your plane is, the more power your plane is producing, that RPM, the more twist, the more torque the airplane wants to go in the other direction. Now, spiraling slipstream. This is kind of a easy one as well. Okay, I'm gonna have my propeller right here. For simplicity, I'm gonna go ahead and remove the wings, because I don't really need this for now for this demonstration. And so, as I said, from the pilot's perspective, the propeller moves clockwise. Now, the spiraling slipstream it's actually creating a spiraling motion of air. Now, since we're actually traveling through this spiraling slipstream, the air is actually going to hit the left side of the rudder. If the air hits the left side of the rudder, what direction is the plane going to go? It's going to go to the left. So that is your spiraling slipstream. So let me see if we can, and there's another good picture of the spiraling slipstream as well in the P-hack. So if it's spinning this way, here's our cockpit right here. Here's our little back window. Here's our rudder right there. So the airplane is going to be spiraling this way. It's going to go underneath, over, underneath, over. Oops, sorry. Over, underneath, over, and then bam. That's where it's going to hit the rudder on the left side, causing the airplane to go in this direction as it's pushing the rudder that way. That's your spiraling slipstream. And last, your gyroscopic effects. So there's two principles in gyros. There's precession and there's rigidity in space. Rigidity in space, if you were to get something spinning really fast, last time you had a top of those old-fashioned gyros, you spun them really fast and you can put them on a string and they just sit there and sit there and sit there until the speed, the momentum stops, and then it loses its balance. Well, the gyro works the same. Well, that's essentially how a gyro works. If you have something spinning really, really, really fast, it's going to remain in space. It's not going to move anywhere. Precession is what's going to be the key here. Precession, all that's saying is, let's say we have a rotating object and we're moving it this way, moving it that way, moving it that way. If we were to apply a force right here, let's say we apply it right here, boom, it's not actually going to be pushed this way. It's not going to actually be felt there on a spinning gyro. In fact, it's actually going to be felt 90 degrees from that original point of force. So let's draw our little 90 degrees. Remember our little 90 degree little symbol right there. It's not going to be felt until right here. Now let's use this principle on our propeller. So as I said, the propeller is spinning clockwise, right? According to the from the pilot's perspective. Now let's say we're in a tail dragger, in a tail wheel airplane. So a tail wheel normally sits back like this. Now let's say you're going full throttle and you're getting to go down the runway, and you don't necessarily want to take off of your tail back there, right? What we normally do is we push the nose forward a little bit to get on our main wheels, and then we tend to just lift right off. It's a magical thing taking off in a tail wheel. But anyway, so that pressure, that force, where we're going from here to here, we're applying a force on the top of the rudder by that rotation. So if we're applying a force here on the top of the rudder, because it's going from here to here, we're applying that force from here to here. We're applying on the top. It's not going to be felt until here. So if we're pushing, it's not going to be felt till 90 degrees of the rotation. So if it's being felt 90 degrees, now where is my airplane going to be wanting to go? To the left. So force is here. It's not going to be felt till here. It's going to be pushed here, and the airplane is going to go to the left. That is your gyroscopic left turning tendencies, and these are all 4 of the left turning tendencies. Do you have to explain it really that much in depth? Not necessarily, but I kind of wanted you to have a full explanation and understand the why of all of the four left turning tendencies in your aircraft. Now with Cessna, you don't really have to worry about too much of the gyros. Don't really have that much to worry about in the gyro for the Cessna. This is mainly just for tail draggers. So these 3, make sure you understand those 3. Again, review these again. Look in the P-hack, look in the aerodynamics chapter to review what you've just learned about the 4 left turning tendencies.